Okay, so James Prescott Joule did a neat experiment. It turns out that if you take water and stir it, you're adding in energy. And when you add in that energy, it reveals itself in a temperature increase. So he rigged up this deal with a couple of falling masses, causing it to stir water. And knowing MGH work, our gravitational potential energy, work that could be done on this water, taking this energy and turning it into heat energy stored in the water, at least temporarily, figured out the mechanical equivalent of heat. And so, turns out that 1 kilocalorie is defined as the amount of heat needed to raise the temperature of 1 kilogram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. And so we have the mechanical equivalent of heat. There's other units all over the place, but let's just get down to the punchline here. Capital Q stands for heat, and it's the energy transferred due to temperature differences. And we can figure out for different substances have different relationships to how much their temperature increases according to how much energy is put into them. So let's step back for 1 second. Heat is energy that flows from a high temperature object to a lower temperature object. When something absorbs heat, its internal energy, the energy of its atoms and molecules, will increase. And when something releases heat, the internal energy, the energy of those atoms and molecules, will decrease. The units for heat is joules, and two things can occur when an object absorbs or releases heat energy. One of them is that there might be a temperature change. Usually we would expect this. So if something absorbs energy, its temperature will increase. If something releases heat energy, its temperature will decrease. Another thing that could happen is that there might be a phase change. So if I have liquid water and I add heat energy, I will increase the temperature of that liquid water up until I get to 100 degrees Celsius. Then when I keep adding more heat energy, the temperature will stay at 100 degrees Celsius as my liquid water turns into steam. But that whole time I'm adding energy and the temperature is staying the same until it all turns into steam, and then the steam will heat up. Alright, so here's an important equation. Q equals mc delta T. This is the case where I have cold water and I'm adding heat to it to get its temperature to increase. When a solid or liquid of mass m absorbs and no phase change is occurring, then Q equals the mass of the water in my pot on my stove times C, that's the heat capacity of water, times delta T, the change in temperature. So we need to talk about this C, this heat capacity idea. Heat capacity is a physical property that relates to how much energy, how the energy absorbed reflects in changes of temperature for a given substance. So the units for heat capacity are joules per kilogram times Kelvin. Metals tend to have low heat capacities, makes them good cooking vessels. They don't absorb a lot of the heat. It doesn't take a lot of heat input to get them to increase in temperature. Other materials tend to have higher heat capacities. Water has a weirdly high specific heat capacity. So before it was established that heat was indeed energy, heat was traditionally measured in units of calories. So we had calories for some things, joules for other things. We didn't know that they were ultimately the same thing. So they are the same thing. nutritional calories can be thought of in terms of heat energy as well. If we do have a phase change, if I have solid ice and I'm turning it into a liquid, then the heat that I add is going to be Q equals ml. I don't have temperature in here because it's going to stay at a constant temperature the entire time that the phase change is taking place. So if I have ice and I add heat to it, that ice will stay at 0 degrees Celsius the whole time that it's melting. So if you get a glass of ice water, what you're drinking is at 0 degrees Celsius so long as there's ice in there. Once all of the ice melts and turns into liquid water, then it absorbs more heat and it warms up. But the whole time that you have ice in your water, you have something that's at 0 degrees Celsius. Doesn't mean you can toss an ice cube into a swimming pool and instantly make it be at 0 degrees Celsius. But if you have it at thermal equilibrium to start with liquid water and ice present, then you will maintain that 0 degrees Celsius until all of the ice is melted. So this is what happens. You add heat to something at a certain temperature. I have cold ice. I just pulled it right out of the freezer. My freezer is set at negative 20 degrees Celsius. I add heat to that ice and the ice heats up. It heats up until it reaches its melting point at 0 degrees Celsius. Then I keep adding heat and the ice will turn into water, and I'll have ice and water present together at 0 degrees Celsius until all of the ice melts. Once all of the ice melts, I have liquid water and I add heat, and the water gets warmer and warmer and warmer until I reach its boiling point. Then I have water and steam together at 100 degrees Celsius. As I keep adding heat, turn all of the water into steam. Then I have hot steam. I keep adding heat and the steam gets warmer and warmer. So that's what happens as we add energy. So for this phase change piece, when I have, so we'll just jump to water here because this is the familiar one. When I have water at 0 degrees Celsius, that's where the phase change will take place. Q equals mLF, latent heat of fusion. So if I have 1 kilogram of ice, the amount of heat that I have to add to change 1 kilogram of ice at 0 degrees Celsius into liquid water at 0 degrees Celsius would be Q equals mLF, so mass 1 kilogram times latent heat of fusion 3.33 times 10 to the 5th joules per kilogram. So it would take 3.33 times 10 to the 5th joules to turn 1 kilogram of ice at 0 degrees Celsius into 1 kilogram of liquid water at 0 degrees Celsius. Likewise, if I then take that and heat it up to its boiling point, then I'll have 1 kilogram of liquid water at 100 degrees Celsius. Q equals mLV, latent heat of vaporization, and I would add 2.26 times 10 to the 6th joules, a lot more energy, 2.26 times 10 to the 6th joules of heat energy into 1 kilogram of liquid water at 100 degrees Celsius in order to turn it into steam at 100 degrees Celsius. That's how this latent heat of fusion and latent heat of vaporization work. So here's some questions from the homework. If I have both the aluminum pot and the water both starting at a certain temperature, then I'm going to do Q equals mc delta T for the aluminum pot. The mass of the pot is 0.75 kilograms. Heat capacity of the aluminum pot, I'd look that up on one of the tables. Delta T, the change in temperature, I'm going to go to a final temperature of boiling water, so that's 100 degrees Celsius, minus the initial temperature of 30 degrees Celsius, so a 70 degree temperature change. So MC delta T for the pot mc delta T for the water, the heat capacity of water is more than that, and I'd figure out how much energy it took in order to bring the pot and the water to 100 degrees Celsius. That's the boiling point of water. And then, in addition, now I'm going to stay at the same temperature. I don't need to heat up the pot anymore, but I'm going to keep adding heat in order to do Q equals MLF. Take 0.75 kilograms of that water and go from 100 degrees Celsius water into steam at that temperature. And so I would figure that out. Some other questions from the homework. All right, calorimetry. So this is a case where I don't know the heat capacity of a substance, some unknown substance, and I just want to figure out its heat capacity. What I'll do is I'll take this rock and heat it up to a certain starting temperature just by having it in thermal equilibrium with boiling water or hot water. Then I'll place it inside a known amount of liquid water starting at room temperature, and then I'll allow those two things to achieve thermal equilibrium, and I'll know that any heat that is gained by the water is represented by heat that is lost. So Q gained by water plus Q gained by object equals 0 if this is all insulated, but in this case we'd have the heat that's gained by the water is the heat that is lost by the object. And the final temperature of the object in the water will be my final temperature. They'll achieve thermal equilibrium, and I'll be able to figure out mc delta T water equals mc delta T object. If I know the mass of water, the heat capacity of water, and the delta T for the water, and I know the mass of my object, but I don't know the heat capacity, but I do know its change in temperature, then I can solve for the heat capacity. It's the only part that I wouldn't know. So there's some typical calorimetry problems that you'll run into in the world. I go through some examples in the homework and all, but so you can look at these, and if you have questions you can ask them. But there's heat capacity, specific heat. All right. So here's some typical values. So water, 4186. It's really huge, high heat capacity. That's why we use it for any number of ways of transferring heat around, and you'll see more of that when we get into heat engines and thermodynamics. Ice has a smaller heat capacity. Steam has a smaller heat capacity. Aluminum down to lead. How much energy you need to add in order to get it to increase in temperature. All right. So heat is energy transferred between objects due to a temperature difference. Objects are in thermal contact if heat can flow between them. Objects that are in thermal contact without any flow of heat are then said to be in thermal equilibrium. That means they're at the same temperature. Thermodynamics is the study of the physical processes that involve heat flowing from one place to another, thermodynamics. If objects A and B are both in thermal equilibrium with object C, then they are in thermal equilibrium with each other. So that gives us the ability to take the temperature of something and say, hey, this was at 30 degrees, this other thing was at 30 degrees. I know if I brought them both together in contact, no heat would flow because they're at the same starting temperature. Temperature determines whether two objects will be in thermal equilibrium. On the Celsius scale, water freezes at 0, boils at 100. Then we have Fahrenheit, a little bit weird. The lowest attainable temperature is absolute 0, so we jump to the Kelvin scale and say on the Kelvin scale, absolute 0 is 0 Kelvin. Water freezes at 273.15 and boils at 373.15. The degree size is the same, Kelvin, Celsius. So we have our conversions. This is stuff from chapter 13. Some of these equations, but now into chapter 14 again. Heat capacity of an object, phase change, energy is conserved in heat flow, and then I just have some other slides from the chapter. All right, good job. You survived chapter 14. Make sure you get the homework answers done.